Okay, so good evening, everyone. I'm going to be taking a class on global and local ideas, or like Globloc. So these are types of ideas in combinatorics. So there are like a lot of the combinatorics ideas you have heard about will fall in one of these. So global ideas are basically considering over the whole problem. Like for example, PHP. Uh, then there is coloring arguments. There is expected value, and local is basically when you are taking over one number. Like, for example, if you want to take the largest number uh, and you want to consider only properties of that number, then that would be a local idea because you're only considering one thing, not the whole thing. For example, greedy, extremal, then smoothing and ideas like that. Other ideas that fall in global are like summing and double counting. So I'll just start with a quick example problem. Um, you have an 8 by 8 chessboard such that every cell is the average of the values of its neighbors. Find so I'll give you a few minutes to try this. Okay, sorry. Yeah, neighbor is sharing edges. If you have any ideas, feel free to speak up or you can message me privately.
I guess we can look for the maximum number in the entire chessboard.
Yep, that's basically it. So yeah, you take the maximum number and this is the average of its neighbors. But since it's the maximum, all of the neighbors are less than or equal to it. So they have to be exactly equal. And so you get every number is equal to this number. So like you can only have one distinct value. So yeah, this is an example of uh, a local idea because you take the you're being greedy and you're taking the maximum element, or like you can call it extremal as well. So yeah, did everyone get this? Did everyone get the concept of global and local first?
Yeah.
Okay, cool. So I'll just post a problem now. Give me a second.
Hi, sorry, can you just give a summary of what happened?
Oh, yeah, basically we just started. So there are uh, two types of ideas, global and local. So global is basically when you're going over the whole problem as a like you're looking at the problem as a whole, and local is where you're looking at a particular part of the problem. And then we did this problem where basically you just consider the maximum element. So that's like a local idea. Okay. Give me a second. I'll just paste a problem.
Okay, so after taking a maximum element, like How did we conclude that the answer is one?
Oh, after taking the maximum element, you basically have that this element is equal to the average of the values of its neighbors.
Yeah.
So, and we know that it's greater than equal to all of its neighbors. But since it's the average, it has to be equal to all of the neighbors, right? So
Okay. Yes. Sir.
basically they're all equal. So like everything is equal. Okay, I'm pasting the problem. Okay, I'll give you some time to think about this.
Excuse me, but can there be non-painted vertices?
No.
Can it happen like all the if n is odd? So can I just color all the vertex with one color itself?
Uh, you can't, right? Because then 0 is an even number. So like the other two colors will have 0 vertices. So
Okay.
okay, any ideas?
I guess we should start by counting the number of isosceles triangles.
Yeah, okay. So, okay, how many isosceles triangles are there?
I've not proceeded to count the entire number, but for like five, it's 15.
I think
For
like
five.
for every two pair of points, there is exactly 1 point, one another point, such that we get a isosceles triangle. Is that right?
Yeah, exactly. And why is this true?
Because n is odd.
Yeah, okay, perfect. So you have that there are a total of NC2 isosceles triangles. Okay, what's next? First of all, does this look like a global problem or a local problem? Like, what are you trying to do?
Feels like a
It
local
looks,
one.
it looks like a global.
It looks global like PHP or
Yeah,
something.
it looks PHP argument.
Looks global.
Okay, that makes sense. Yeah, it is a global problem. So what do you want to do next now? Okay, so notice there are three types of triangles, right? One triangle has all vertices same color. Then one has two vertices same color, and one has no vertices same. And we want this is the type we want. So can you prove that this definitely exists?
Wait, what about double counting? Like we count the number of triangles each colored vertex is in.
Yeah, perfect.
Number
So
of
how do you
isosceles
proceed
triangles.
with double counting? Does anyone have any idea of how to double count? Double counting is the correct idea. Okay, let's start with how many triangles will be there of this type.
I mean, it depends on the. Okay, wait. How?
Okay,
Like if
call
you
this type.
consider, yeah,
Yeah.
so like suppose you have like the you have one color, you have n minus two times, and the other two color you have one time. So you, I guess you will have n minus two c two times the max. So it's
So,
less than equal.
but why do you going like for a single case? Like we have to consider over all possible colorings.
No, I'm saying it's like less than or equal to n minus two and equal to two.
Yeah. Okay. Yeah.
Wait, do you want an explicit form in terms of what?
No, not an explicit form. I mean, not of this particular. Like, assume there are X triangles of this type and Y triangles of this type. So, can you find any something that will give us, like an equation for X and Y? And you have like Z of this type. So, you want Z equal to 0, right?
Yeah.
So, first of all, you know that X plus Y is equal to NC2, right? Because there are these triangles and there are total these many triangles. So,
Yeah.
Yeah.
This is by assuming contradiction, right?
Yeah, by assuming contradiction.
Like, can we go towards a mod contradiction or something like parity stuff?
Parity stuff, yes, probably, but how would you approach that?
Like, okay,
You
we
don't,
consider some vertex. Oh, sorry.
yeah, go ahead.
So we consider some vertex, and then we like find the number of isosceles triangles with that vertex as the, what do you call it? Top vertex? I don't know. So
Basically, the vertex which is not in the base.
yeah, not the
N
base.
minus 1 by 2, that should.
Yeah, n minus 1 by 2
Okay.
triangles will be there. So mm,
But then you basically get that, I mean, each vertex has n minus 1 by 2 isosceles triangles, but so what? I mean, you're not getting any contradiction, right? Because, I mean, it, what if like n is equal to 13? Then like there are 4 triangles of this shape, and that's like even. And if you have like n equals 7, then it's, oh,
Wait, I guess I might have.
did I mess up? Okay, this has 6 and this has like 3 triangles from each vertex. So like,
Wait, can we consider like red, like consider the colors to be red, green, and blue? Then RC2 plus GC2 plus BC2 is like the double count for the number of isosceles triangles.
yeah, perfect. Okay, so you have AC2 plus BC2 plus CC2. Okay, now what is this double counting giving us?
The number of like the isosceles triangles, because like we are consider there's one isosceles triangle with the following base with the two same colors.
Actually, that is not true because like here, AC2, you are considering the same color base, right?
Yeah.
Like you're not considering isosceles triangles with the base of color A and color B.
Wait, what?
Like you have this point, right? Like these 5 points, and you have R, G, B, R, G. So like you're basically AC2 is going to count the triangles with this base, then BC2 is going to count the triangles with
then AB you can
this.
take, right?
Yeah, exactly. You can take RG, and that is not counted in any of these.
Or
So like
yeah.
this is
Like, no, we can count it by putting term AB, A into B, because that'd be the number of, wait.
A into B, yeah, but okay. So you have, but then this is just the total number of edges, which we like already have. These two are equal. So, I mean, this is kind of redundant. What are you going to do with this number? Okay, let me get you started. So we have, so far we've been considering that only the base, right? But what if you consider a leg of the triangle? Like for example, you have an edge that has red and red. So now this is part of 3 triangles itself, right? Can you see why this is true?
Wait, I can see two triangles. So if you can assume the first R is a vertex, then the other R and there is a corresponding point.
Okay, wait, let me draw a polygon to make it easier.
So the third point could be red, green, or blue. So three triangles.
Okay, for this edge, can you see three triangles? Wait, are there three? Okay, yeah. So there's two triangles, but like, so this leg is, like, what can you say about this leg?
Okay, yeah, in one place it acts like a base for the isosceles triangle, and one time and two times it acts like
A
the
leg.
side line, the equal side. Yeah.
Yeah. So basically, every single edge is coming in three different triangles, right? So now what we have is, what we've taken is we've taken your thing of AC2, BC2, CC2, and we have converted into this thing where all the monochromatic edges are giving us three different isosceles triangles. So now what will this quantity be equal to? Like, it's given that you have a monochromatic edge. So what's next? So if you have a monochromatic edge, it will definitely be part of one of these triangles, right?
Yes.
Yes, so like 3 times this value.
Yeah,
Like
three
the number of
times.
isosceles triangles. Number
Yeah.
of these type of
So
isosceles triangles.
So basically, if all vertices have same color, then it will be counted thrice, right?
Yeah, thrice. So 3 times this.
So like, um,
that's going to be like the number of isosceles triangles with two colors plus 3 times the number of ones with monochromatic triangles.
yeah. So basically, 3x plus y, right?
Yes. Wait, did we define X? Oh, you're right. Yes.
And like, there is a 3 over here because we're counting each edge in three different triangles.
Right.
Y also must be divisible by 3. And then, but n is like coprime to 6.
Y is not relevant to n. Okay, but we're basically done here. So now we move on to this, right? We have these two things. So this
But
is
right now
basically,
it's a parity issue.
yep. And we're like, yeah, we're done basically. It's a parity issue. So you have this minus this is even, and that is like a contradiction. There is some algebra stuff. I think it's like AB plus BC plus CA is even. You get something like that, which is like false.
Wait, can you explain the 3x plus y part again?
Okay, so like, you are considering every monochromatic edge. So these are the total number of monochromatic edges, right? And each edge is coming in three different isosceles triangles, exactly three. And we know this because n is coprime to 6. So like, this is the total number of triangles of monochromatic edges. And we know because we have assumed that there is no triangle with all three different colors. We know that every single triangle has a monochromatic edge. So like, every triangle will be counted in this thing. And if you consider a triangle with all vertices of the same color, that is the number x, so this will be counted three different times, right? Because it has three monochromatic edges. And a triangle that has exactly one monochromatic edge, which is the type y, will be counted exactly once for the edge that it contains. Do you get this part?
Okay, yeah, make
So like, we get this equation.
Okay, so we can generalize to not only z is equal to 0, but also like just z is equal to even. That will also give contradiction because it's just parity, right?
Yeah, because you have like, you have a plus b plus c, c2 is congruent to mod 2, and like, this gives a contradiction. I mean, do you really want to do the calculation? So did you guys get this problem?
Yes. Yeah. Makes sense.
Yes, makes sense.
So we used double counting. Okay, and we have used extreme. Okay, I'm giving another problem now. You are given a sequence a1, a2, an of positive integers such that 1 is equal to a1 is less than equal to a2 less than equal to. And you are also given that and yeah. So you need to prove that you can split. Okay, before we start this, everyone is clear with the this earlier problem, right?
I didn't get the
Yes.
parity issue. Just
Oh, okay. Let me like okay. You get
yeah.
then this cancels out, and you have like
But wait, isn't this all going on mod 2?
yeah it yeah it is going on mod 2, but like you are kind of
Like if you're canceling it out, you're like technically multiplying 2 on both sides.
okay, wait.
Yeah.
Let me explain it a different way. Oh, wait. You have like oh, wait, no, it would become mod 4, right? If you multiply 2. So like yeah, it works out anyway. So you have n squared minus n is congruent to a square minus a plus b square minus mod 4. And then you have this basically expands. So you can cancel these out because n is abc, and then you have a square plus b square plus c square plus 2 ab plus bc plus ca is congruent to a square plus b
Yeah,
square plus
fine.
c square mod 4. And now you can like see because
Like canceling the 2's itself would be like making the mod 4 mod 2, right?
yeah, but then you have ab plus bc plus ca is congruent to
Yeah, you'll
2
have
mod.
twice of AB plus BC plus CA is congruent to like 0 mod 4, 0 mod
Yeah,
2.
no, you have twice of ab plus bc plus ca is 0 mod 4 because like when you go from here to here, you're multiplying 2.
Okay,
Like for example, if this was 1 and this is 1, then you multiply 2, so like they both become 2 mod 4, right?
correct.
And if this was 0 and this was 0 and you multiply 2, then they both become 0 mod 4.
Fine. Okay.
Yeah,
Okay, I see. Oh, okay, yes, I got it. Yeah.
okay. Cool. So try this problem.
All integer, all natural numbers. Yeah.
Yeah,
Oh, interesting observation. I think EI can be a first 10 primes.
we can. Okay, yeah, because of Bertrand's.
Yeah, Bertrand's.
That's cool.
Sorry,
Okay,
by what again?
that's actually not relevant. Like Bertrand's basically says that between n and there exists a prime in between in this range.
Oh, I see.
No, wait. How can it be prime? One is not prime.
True. Also true.
I guess this is global.
Why?
Like,
Like, okay,
um,
global has these kind of ideas. PHP, yeah, what do you think this would have fallen? Or like,
like, like. Oh wait, this is greedy. Okay, I guess so.
okay,
Yeah,
why
it's
is
true.
it?
Yeah, because we can just keep on taking unless we get more than double the sum of the entire set. Like, what I'm saying is that you get A1 plus, like you sum of them all, A1 plus and so on till the end, and you get the sum. So you can so what you do, you just keep putting in numbers till you get double, unless you reach half of the sum, and this other part will go. Like this is a base, like a very rough idea for PDAs.
So you're saying like, let me give you a sequence and you can like tell me what you want. So yeah, what are you going to do?
Yeah, so what I was saying is that, so first if I sum the entire sequence, so you get a sum. So in a set, but I will just be greedy and I will just take in numbers till I I'll just take in numbers till I get half of the sum of the entire sequence. Something like
But
that.
what if, I mean, what do you mean like you will get this half of the sum? Like, okay, or the sum of this is 14 plus, I think it's 62. So like half is
Yeah,
31.
yes.
So now the sum of this, the first term is 1, then 3, then like 7, 14, 25, and whatever, 43. Okay, what is your idea? Like here we're not getting, like we're directly passing 33.
Mhm.
But yeah, I mean, you're thinking in the right direction. Just make it a bit more, better algorithm.
Like
Yeah,
first,
greedy
uh,
algorithm is
like can we just try to first take the maximum? Like first we put in the maximum element
Okay,
and like. So like suppose we get 19 and then we take the second maximum value, like 18, but 18 can't work, so we just go back and do like this. So here you will get 1, 11 and 19. So if you just follow this.
okay. What was Riddhiman saying?
no. I was just saying greedy algorithm. So I think like we divide into two groups, and in the beginning we just like assign arbitrary AIs to any of the groups, and then we devise an algorithm where like if the say group one has some greater then I think there must be like an algorithm such that we can switch one of the AIs, and then the difference between the two groups will be lesser and lesser, and then that way the difference should approach zero. That's like the main approach I was
You're
thinking.
basically saying Aryan's idea, right? Because he's taking the maximum and then he's taking the next maximum possible that fits in the set. Like basically you're taking the maximum element and then you're taking the largest element which will fit, but it's also less than half or less than
Yes,
equal.
yes, yes.
But yeah, wait, but just looking for largest might not work.
Why not?
We have to prove that this algorithm will give us the result, right?
Okay, first of all, we don't know that this algorithm will give us. I mean, intuitively looking at it, it seems like it should give us, and I mean, it is the correct algorithm. But how are you going to prove that it will always give half, exactly half? Like, okay, what if I like use this greedy algorithm and at the end it is going to be like, what if the at the end the sum is like 30?
We just add one, right?
Sorry?
Wait, we just add one, right? Then
No, no, like not in this case, but like in general, like what if there exists a sequence of numbers such that uh, you take the maximum possible thing and at the end it is still less than half. Like you have taken one as well. Can you prove that this does not happen?
So there must be like something bigger than the last element which you chose. which
I
just
think
makes it equal.
I think we can for this thing we can have to use that 2 AI less greater than equal to AI plus one. So no,
Okay, how are we going to use this?
like suppose like this is just a rough idea. I don't know if it works. So if I just write A1 2 A2 or two like the sequence says A1 2 A like no okay so I like I would be like that if it's the first element is A1, the next element would be less than or equal to 2A1, and the third element would be less than or equal to 4A1, and so on. So if
Okay,
you go on like that and sum them up, then I guess you can guarantee somehow things something like inequality. I don't know.
okay. So yeah, that is the correct idea. It's not exactly that, but basically you have like AI plus AI is greater than equal to AI plus 1. But you also have that 2 AI minus 1 is greater than equal to AI. So you basically get that 2 AI minus 1 plus AI is greater than equal to AI plus 1. And then you just keep extending, like expand on this. It's like again you get 2 AI minus 2 and so on. So at the end you get 2 A1 plus A2 plus A3 plus and so on plus AI is greater than equal to AI plus 1. And since you have A1 is equal to 1, you get 1. You get this. Okay, so now we have this inequality. How are you going to use this?
So it's like if we now like after we got this, if we apply the same algorithm, does it work? So
What do you mean?
like we got this, now we just take the set and first take the maximum element in that set and continue. So, does that work this time?
I'm not getting what you're saying. Like you have
No, like
taken a
we
set
had
of
an what I'm saying is that we had an algorithm, right? That we take the maximum elements and we somehow hope that it receives half, but we need to prove that it will get to half. So
yeah.
does this? So can we use this inequality in the prove that and use the same algorithm?
How will you use the same algorithm? Like where are you using this algorithm now? I mean, you use the algorithm to get the set, right?
Yeah.
So now what are you going to do?
It's by that it means that like whatever AI we add is going over that midpoint or middle. Like after we get the set, like whatever smaller AI we add, it's going
Yeah.
over the half of it.
Yeah. So basically, you're saying that the AIs that we do not include, adding any of them will give you over half.
Correct.
Yeah, that's the idea. How can you expand on this?
One example of the sequence, I guess, is the powers of two.
Yeah, I mean, powers of two is a sequence. I mean, sure, but like the sum of powers of two is like odd. So
So wait, so we have like summation of that set plus some ax is greater than n by 2, right? So, I mean, whatever the sum is, sum of ai by 2.
yeah,
But the summation of the set plus that ax is less than equal to 1 plus a1 plus a2 plus a3 till the ai, the a of x minus 1 plus that summation of the set.
yeah.
Okay. How to use that?
Okay, wait. So I think Siddharth said this before, but basically he said that if you don't have one in the set, you can take one, right? Like for example, if you
Yes.
have if a s like if a1 is not part of s and the sum of s is less than half, then you can always add a1, right?
Fine.
That makes sense to everyone, right?
Wait, could you repeat it again?
Like basically assume you have this, like you have used this greedy algorithm to get a set. This set is s, and let's say that a1 is not in the set, right? And now what you have is that the sum of the all the values in the set s is less than half. Like it's strictly less than half. So you can always add a1 to make the sum greater by 1, right?
Oh, yes, yes.
Okay, so that implies basically that a1 has to be in this set.
Yes, yeah.
Okay, so can you go further with this somehow?
Hmm.
Okay, what can you say about a2? Like is a2
Two
in
is
this set or
either
is it
two or
not?
one.
Sorry?
A2 is either one or two. Wait, I don't know about the set.
No, 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 not about the value of a2. That is irrelevant. But is a2 in this set or not?
I'm guessing it is not, although I haven't seen how exactly it is. I'm guessing
Okay,
it is.
assume a2 is not in the set, right? So what can you do? Like if a2 is not in the set, then like you basically have that let me call the sum of this set as like I don't know k. So then you have like k plus a2 is greater than
N by, okay,
by 2,
s by 2.
and you have k is less than s by 2. But you also have that a1 is in this set s.
Right,
Okay, so now basically what you get is that you also know that 2a1 is greater than equal to a2, but a1 is equal to 1. So basically you have like 1 plus a1 is greater than equal to a2. So what you can do is k you can force A2 to be included in this set by doing K minus A1 plus A2. And the sum will increase by at most 1, right?
Correct.
Correct.
And since you have that the sum increases by at most A1, you have that like it will reach S by 2. Or if it doesn't reach S by 2, then you can add A1 again. Because A1 is 1. Okay, let me explain it in a better way. So you have this set 1, 2, comma, blah, blah, blah. And you have a value n such that n plus 2 is greater than s and n is less than s. So what can you say about s? Like s is equal to n plus 1, right?
Yes. Yeah.
Okay.
It's integer.
Yeah.
Yes.
And so then you also have that n is made up of some integers like a1 plus blah, blah, blah. And you have a1 is equal to 1. So if you take n minus 1, like n minus a1 plus a2, you know that from this inequality, we have that 1 plus a1 is greater than equal to a2.
So it
So
must be at least
1,
n plus 1.
2 minus a1. So if you perform this operation on n, then you get like this is less than equal to n plus 1. Do you see the point now?
Okay, that makes sense. Okay, nice.
Yeah. So you have n minus a1 plus a2 is less than equal to n plus 1. So you can always remove a2. Like if a2 is not in the set, you can remove a1 and add a2. But then again, you have that a1 is equal to 1. So you can always add it back. So at some after one of these operations, the sum should become half.
Yes.
So you have that a2 is always in the set. And now we can just keep on extending this. So like more formally assume that ak is the minimum element such that it is not uh, such that ak is not in S. That means you have one a1, a2, and so on till ak minus 1. These are all part of S. And if you want to make the sum, and the sum is less than half. So what you can do is you can remove all of these elements and you can add ak instead, right? And assume this sum is like still less than half. Sorry, assume the sum is still less than half. You can like add a1 and then you
A1,
can
yeah.
and so on. So yeah,
Oh,
basically
we
that's
always have a way to increase the sum one by one. Okay, yeah.
yeah because of this inequality. So yeah, basically you get at some point there is a contradiction and like all of the elements are in S, which is like just false. Uh, so yeah, that was a greedy problem. Then there is an alternate solution to this, which is like I'll just tell the idea. I'm not going to explain the solution. You can work it out later. You have two piles, 0 and 0, and you can like take an and you add it to a random pile. So like you add it over here, and then you take an minus 1 and you add it like you add it to a pile which makes sure that the sum of either pile is less than half. So for example, you add it over here. So now again, notice that the difference between the two piles is always going to be less than like an minus 1 is always going to be less than an minus 1. And then you just keep adding, like if you add an minus 2 here, then you again have that an an minus 1 minus an minus 2 is less than equal to an minus 2 from this earlier inequality. Oh, from this one. So
So
yeah, that
that
is,
will go all the way till A1, the right column.
yeah, and a1 is basically 1. So yeah, that's an alternate solution, but it is again involving a similar greedy idea. But yeah, okay. Everyone got this problem. Does anyone have any issues?
No, I
What was the source of this problem?
Okay. Oh, I think I should have told the source. Like, okay, this one is ISM 2016 P3. Oh, this is some old problem, some random problem which I found. Okay, wait, let me paste another problem. Have any of you seen this problem?
haven't.
Okay, I'll just give you 5 minutes to try.
By the way, like in general, is are most grid problems local?
It depends on the type of problem. Like a coloring problem is always going to be global. But then, for example, the problem we did in the start, the problem of the average, the cell is an average of its neighbors, that is a local problem.
No,
So
coloring problems are global.
yeah, coloring are global because you want to find some like argument over the sum, right?
Just asking, but are the constants here just arbitrary?
Yeah, they are irrelevant. I mean, there are some properties of 2022, but like it's just because like it's a problem from 2022.
like 2022 square minus 4.
Sorry? No,
The
it is
answer
not.
is
It is not n square minus 3.
what?
Okay, do you guys have any ideas? Do you think this is global or local?
Hello.
Global, I think.
Yeah, okay. What do you think is the value of, you guys read the problem? Like, I mean, you guys have worked on it a bit. Like, what do you think the value of k is?
I'm not sure, but I'm guessing half the number of like squares in the board.
Okay, assume like, forget 2022, assume it's like 6 by 6, right? You have this. And forget this 10 to the 6, that is also like pointless. Make it like this, say just, I don't know, 15. Okay, so now what can I say about this board? Like the gardener is going to choose a 3 by 3 square and the lumberjack can choose any 4 different squares. So like, what now? Okay, first of all, somebody said half. So how are you going to ensure half?
Like you split the grid and then you. I've not really concretized the idea. Wait.
Yeah, I just the general idea. How are you going to split the grid? Like, okay, if you notice 3 divides 6 and 3 divides 2022.
Like you split it into that many 3 by 3 grids and then.
Exactly. So you have this and you have this. Okay, and now what the gardener is, the gardener will make 9 squares taller at once, right? Like by 1 unit. And the lumberjack will make only 4 squares shorter by 1 unit.
Yeah.
So now if
Right.
you take this cell and like you perform the operation on this cell, like, I don't know, 10,000 times. So what you eventually get is like some 5 squares must have a certain height, right? Like what will that height be? I don't know. But it's definitely going to be like larger than, say, wait, let me like do the calculation. Oh,
I
Yeah,
think
like you have to
it
take
would be like
into
5.
account how the lumberjack and gardener will circulate around those 4 squares of the nine.
yeah, I mean, we don't care about the 4 squares of the line. Like we just, I mean, if the lumberjack decides, he can just choose the same 4 squares every time. Like we can never increase their height. But what
But
we
5
can,
we'll definitely, I think we can do. So like 5 in each of the 3 by 3 squares we should be able to do.
yeah,
So
you
just
can,
guessing, would it be like you have 5 in each cell? So like I don't know, 5 n square.
yeah. So basically, like, you have 36 cells and you have like 4 3 by 3 cells. So in each you can do like,
5, so like 20.
so basically, if you have 3n by 3n grid, you can make what, 5n square?
Yes.
You can always guarantee this because like you just increase the height of this like 10 to the 10 times, then you again do this like 10 to the 9 times because like, by the time you finish this, the 5 trees in this one will still be above 15 centimeter, 15 units, whatever. And then you can do this 10 to the 8 times and like this 10 to the 7 times. So like after all of these operations, you can guarantee that every tree which was originally the tallest will like, okay, how do I formalize this? Okay, the minimum, like you are increasing, if you're performing 10 to the 10 operations on this, so you're increasing the height by 9 to 10 to the 10, the total height. And in this much time, the lumberjack is decreasing by this much, which is basically 5 into 10 to the 10. And you know that this is the total height, and also that nothing is greater than 10 to the 10.
Can you explain how we can even make like 5 greater in each square? Like, what if the gardener cuts after the first move, the gardener cuts first 4, and then after the
Like
second
obviously,
move, it cuts second 4. So, like, there's an even distribution, but it's not like one is growing a lot.
see, you have one like this, and then the gardener is, let's say, cutting these 4. Then on the next move, you're getting 2, 2, 2, 2, 2, and 1, 1, 1, 1. And he's cutting here. You're saying this, right? This is what you're saying, right?
Yes. Okay, so maybe like when he does this, keeps doing this, ultimately, like, okay.
Yeah, basically that's where you use this argument, right? You have that, you have that the total height after 10 to the 10 operations will be, you have added these many and the lumberjack is subtracted these many. So at the end, the total height is this, and you also have that nothing is greater than 10 to the 10 because you have increased by at most 10 to the 10.
Okay, I get it.
So like either,
So
uh,
after what you said, you start by going 10 to the 10 times over there on the first cell and do that with all the 4. Then in the end, your kind of total would be 5 times 10 to the power 10 plus 10 to the power 9.
what?
5
This,
times 10 to the power plus 5 times 10 to the power 9 plus 5 times 10 to the power 8 plus 5 times 10 to the power 7 after you finish going through all 4 cells in the manner you explained.
yeah, basically like, I mean, the numbers are irrelevant, but basically at some point of time, there will be some trees with a very large height A. Then here again, there will be, you take this number smaller so that it does not interfere with this. It's
So it
basically
just needs to be smaller than 10 to the 10.
yeah, smaller than the height of this thing. Like, or let's say after a certain number of moves, you have ensured that this every 5 of the trees in this cell have a height of 10 to the 20, right? So now you want to perform moves in this. Let's say you perform 10 to the 18 moves. So after these 10 to the 18 moves, if even if the lumberjack had acted on these trees only, their height would be like 10 to the 20 minus 10 to the 18, which is like way larger than 10 to the 6, right?
Right.
But also the 10 to the 18 ensures some minimum height in this, which is like of the order 10 to the 17.
Yes. Yeah.
So basically then you perform 10 to the 16 operations here, and over here you perform 10 to the 14. So at the end, you have eventually ensured that this all of these are greater than 10 to the 6. Like have 5 trees greater than 10 to the 6.
Yes. Yeah.
Do you see the point now? Like why we can ensure that 5 is there in every 9 cells?
Right. Okay. That makes sense why 5 and squares there. Yeah.
Okay, now how will you prove that this is the maximum? Like, is it the maximum?
Like, the gardener can always ensure their fire, like, for every 9 things the guy grows, you can just decrease the 4 lowest ones.
Uh, how are you going to prove that this works?
Wait, how do we
I mean, like, what is a more formal
like
way to say this? I mean, it's the correct idea. Yeah, what were you saying?
yeah, how do we even know that 5 square is the maximum? Why should it be more than that? Like, what's the thought process for that?
Like, you are supposed to prove that it is the maximum.
Yeah, but like, how can we like? Why would we think that it's the maximum? Why would we, like go for getting more?
Your voice is actually very low. Can you type in the chat?
Of
Oh no, we don't think it is maximum. I'm asking you, is it the maximum? Can you prove it if it is? But the intuition to think that 5 n squared is the maximum is because 9 minus 4 is 5, I guess. Like the gardener is increasing 9 and the lumberjack is decreasing 4. So like 9 minus 4 is 5. Okay, Anudeep, can you formalize your idea? Like if you're saying the lowest, you will subtract from the lowest, then that would be 0, right?
No, like the lowest in the 9 that he grows in the previous step.
Okay, yeah, that's that's basically it. Because then, if you're ensuring everything is the lowest, then it will always be 0. Like
Okay,
initially, you
so
will,
in this case, exactly 5 will grow for each n. Like for
yeah.
okay, yeah.
What Anudeep said is correct, but like a nicer argument to make, I guess, like which is not hand wavy, I guess, would be you color it with 9 colors, like you number it 1, 2, 3, 4, 5, 6, 7, 8, 9, and notice that no matter what 3 by 3 square you select, it always contains exactly one occurrence of these numbers, 1, 2, 3, 4. So what you can do is you can just always remove, or you can always cut the trace from 1, 2, 3, 4, and that basically finishes.
Right, I see.
Yeah, nice.
Does everyone get?
I don't get like how he gets 5 in each. Like I got, why do you have to ensure that it's decreasing the order of each of the moves done in each grid? I mean, divided
I mean,
grid.
that's just a construction. Like we just want to, we are increasing this, but we want to know that in this grid, he doesn't manage to make the one of the tree's height less than 10 to the 6.
Sorry.
Like let's say you have like only 4 cells and uh, let's say you have only this size grid, right? And you are increasing every 2 by 2 square and he is decreasing exactly 1 square, right? Sorry, let me make this a bit bigger.
Okay, fine.
So you want to ensure that in every 4 by 4 cell, at least 3 are above some certain limit. Like let's say the limit
Yeah.
is okay. So now you will increase this 1, 1, 1, 1, and then you will make this 0. Then you will make this 2, 2, 2. Like at some point of time, you make this, let's say, up till 5, 5, 5, and 0. Okay. Now you want to perform similar operations over here. So you again manage to make this 2, 2, 2, 2. But in that time, the lumberjack has made, you perform 2 operations here, but he performs 2 operations on this one, this becomes 3. Then again, you perform 2, 2, 2, 2, and then he makes this 1, which is bad for us, right? Because
Yeah, it falls
currently,
below.
yeah. So basically, you make this to a certain limit, and then you perform operations on this, which is like less than this value.
Okay, to like remove his chances of like reducing it too much.
Yeah, basically, you ensure that they are forever.
Okay, got it. Yes.
Okay, does everyone get this problem?
Okay, got it.
Yeah, me
Okay,
too.
okay, nice. We did coloring. Nice. Okay. Now there is one very nice problem. Let me just Find it. I'll paste it.
Which problem was this one, by the way?
This was ISR 2022 C3.
Oh, nice.
Okay, yeah. So I'll give you till 8:20 to try this. I think we are short on time. You guys are fine staying till like 8:45. Right?
Yeah, I'm fine.
Okay.
Me too.
Wait, so like if you take like n equal to 2 and like you color the diagonal only, like that's that. So like is it already partitioned? Like only one of the diagonals should be color, I mean taken, but is it already partitioned by this
Like,
definition?
let me rephrase the problem in a better way. Like you need to assume they call this a domino, but not a domino, but like a tile.
It's like we have to cover the seed.
Yeah, you have to cover everything.
We have to
Wait,
cover it. Okay, yeah.
let me just check the answer. Wait. Yeah, you have to assume it as, yeah, it's like a tiling. Yeah.
So in this case it'll be 2 by the tiling thing.
Yeah.
Well, I guess lower bound, I think n minus 1 is a lower bound. Like at least n minus 1 sticks when the removed cells are all in a single line.
They can't be in a single line.
Oh
Uh,
shit, I did not read that.
What about like breaking our like grid into smaller and smaller grids? Like we take like an n into n or whatever.
okay. You have 4 by 4.
By force, like
Yeah. So what are you going to do with this? Oh,
you can color like one of the. Okay, just take. There'll be like one. Okay, fine. Yeah. So now Right. So look at the first row and the first column. We need three sticks to like do it.
First row and first column, like, yes. Okay.
And then like the rest just is like a 3 by 3 of some sort.
But is it a 3 by 3? Because like you have this 3 by 3, but it has only two cells which are not there, right?
Okay, yeah, right.
Okay, it's 8:20. So, any ideas on what to do, guys?
Wait, first we can do that to n is like the minimum.
Sorry?
Then we can first we have like
Oh, wait, type in the chat. Your voice is like still quite low.
okay,
What you're saying, MA is greater than equal to 2n.
we first prove that MA is at least 2 and then we prove that MA is at most 2.
I mean, MA, what you said earlier was correct. Like, MA is invariant. Okay, so you can, first of all, you can form a definite lower bound, right? First of all, did everyone understand the problem completely?
Yes.
Okay, because like I had to read it a few times to complete. Uh, so basically you have like, let's say you have this kind of, I don't know, a random arrangement. So now what you can guarantee is that M of A is less than equal to 2n minus 2. Because you can just do in the direction of everything. You can always do it vertically like this, and in n minus 2 rows, the removed cells are like, sorry, the removed cells are not on the edges, and in 2 rows, the removed cells are on the edges. So this, each of these will give you 2, and this will give you 1. So basically, you get this as an upper bound for MA. Okay. But can you prove that this at least this much is required?
I think I got an idea. Like it's not exactly related, but it's regarding this the removed cells. So if we take removed cells for wait, I have a 4 by 4. I made a 4 by 4. So if we have removed cell in row one column one and one in row two column three, then
Wait,
just,
wait,
then
wait,
we
hang
can
on.
switch the then we can switch the row numbers and it would still be a valid
Sorry, repeat. You have?
for example, there's a sieve in row one, column one, and there is another sieve in row two, column three. So when each sieve, we can keep the column same, but we can just switch the row numbers. Then it will
Yes.
give us a valid configuration.
Yeah, it does.
So I think that using this swap thing, we can go from any configuration to any other configuration, like
But
intuition.
can you guarantee that MA will be the same for both of those configurations?
Like because it does not exactly like disturb a lot, like it's
It actually does, because like what if you have something like I don't know, you have a tile over here and here. So you have a tile like this in the original thing and a tile like this. But now when you're changing it, this like you're sending this one over here, right? You're sending this over here. So that will disrupt some stuff.
well, it might not disturb because if both of
Might not, but in this case it definitely does, right? I mean,
I
how
mean,
can you
it
get
does disturb, but the number remains same, right? If we look at only those two columns, say
does it
assume we are keeping the column of each of the sieves the same. So like we are coloring it like covering it row wise. Then like if we are taking only one stick to cover the upper wala row, then after the swap we will take only one stick to cover the niche wala row. Something like that. So the number remains same.
but then there is this and then this.
No,
So
no,
if you're
I'm saying ki we are coloring like only row wise.
okay, you're coloring row wise. Okay, but like
Like you said, we can get 2n minus 2 only doing row wise. So we
yeah,
just do row wise. Maybe this
I
way.
mean, for that specific coloring, yes, but what if that coloring is not the best coloring? Like the row wise coloring there might be something better, right? Can you prove that there is nothing better?
No, I mean like we can get 2n minus 2 doing row wise and then we prove that.
Yeah, but you want M of A to like MA
Oh,
to
is
minimum number of sticks. So
minimum, right? We are not proving minimum.
okay, I'll just like go ahead with the solution. Basically, what you're going to do is you're going to consider a random cell. So whoever said induction was actually correct, but your idea was slightly wrong. Basically, you cut this row and this column. Okay. And what you notice that uh, the remaining thing is basically a 4 by 4 grid. Like you can change it to something like this. Uh, this is like gone and this is gone. So there would be a cell here, one here, and one here. And notice that these dots will always satisfy the conditions because like all of them are in different row and different column. And also now the tiling is the interesting part. So basically, if there is a like notice that this tile is getting cut off, right? Like this one. So it will basically become a tile like this because you're removing one square. So this
What
will
if there's
become
a
like
tile along that row? Like,
then that tile is completely removed. So that we don't need to consider that tile, right?
okay.
Yeah, because like there's literally nothing here. So like what you're going to do with it? You can just delete it. And that's basically the idea. Okay, so we'll induct. We know that M of like, because there is only one possible arrangement, which is this, and that
Yeah.
requires two terms.
Okay.
Now, what we'll do is we will assume that M of A is less than 2n minus 2 for n greater than 2.
Okay.
We know
Now,
that,
what,
right? Like, okay, we are taking a contradiction. Yeah, sorry.
yeah, we know this, like we know less than equal to, not less than. Okay. So now what we want to do is if we have we want to prove from here that M of A is less than 2n minus 4 for n minus 1. We want to prove that this implies this, which will finish the problem, right? Because then that
Yes,
would
yes.
imply that M of A is less than 2 for n equals 2. So what we want to do for this is that we want to remove a row and column such that two tiles are getting completely deleted. Like somebody said, right? What if the tile is along the row? So that is actually a good case because then you are deleting that entire tile when you are deleting the row and column. Do you see what I'm saying?
Yes, yes.
Okay, first of all, did everyone understand how the induction is working?
Yes.
Okay, so yeah, you are deleting a row and a column, and you are getting, you want to show that, uh, okay, and notice that no matter which of these removed cells you will delete,
You can't delete two. You can only delete one in this. Okay, no, you can delete the last one, right? The last
yeah,
row.
what we want to show is basically that, I mean, what you have is basically no matter which of these cells, row and column you delete, there will still be n minus 1 removed cells, and like basically the conditions for n minus 1 grid will be satisfied. You guys see that, right? No matter what we do.
Yes, yes, it should be satisfied.
Yeah. So now all we need to prove is that there exists a removed cell such that it has um, two tiles, like one in its row and one in its column. Because then that would prove that M of A for that one is less than 2n minus
Wait, could you repeat the thing we have to now prove?
4. Which part?
Like, what was the part that we are still left to prove it now? Could you just repeat that?
Okay, we have shown that M of A is equal to 2 for n equals 2. We
Right.
want to prove that M of A is equal to 2n minus 2 for n.
Yes, yes.
So now what we are doing is we are assuming that this is true for some n. So we want to prove that this would imply it is also true for n minus 1.
Uh-huh.
So like induct backwards. Okay, okay. So how?
Yeah, like assume M of A is equal to let's say, I don't know. Let's just say 7 for n equals what should I take as n? 5. Right. Then that would imply we want to show that this implies 5 for n equals 4, which will imply 3 for n equals 3, which would then imply 1 for n equals 2, which is like pause because we have it's 2 for n equals 2. Do you see?
Right. Yeah, yeah.
Okay. So now that is what we wanted to prove. So what we're going to do is we're going to select a random cell, like a random removed cell, and we're going to delete its row and column, which will give us the required n minus 1. Now, all we
Right.
need to show is that for some of this one, like, we want to show that there exists a cell such that when you delete its row and column, it will delete two tiles or more than two tiles.
What about considering all such deletions? Okay, that'll be the same thing we are
I mean,
trying to
you're,
do.
yeah, basically. Okay, so now we just want to prove that, okay, now consider every tile, okay? Now every tile has some point in its row and column, the row or column. Like this tile has this point in its column. Then okay, I should make a better thing. Like you have this. So now this tile has this point in its column. This tile has this point. This tile has this. So notice that this tile, this point has two tiles in its row and column, right?
Yes.
Okay, and notice that
Each tile has at least one end point.
yeah, each has at least one endpoint, and basically you have that n plus 1 is greater than n, which is quite important, because then all we need to show is that there exists at least n plus 1 tiles in total. So then there will be, by PHP, we have one point which is having two tiles originating from it, and we can delete that. And do you guys get it?
Oh,
We have to
right.
prove that
Okay,
we
that
need at least n plus 1 tiles to start
Yeah.
off.
And that is, I mean, basically
Yeah.
trivial. Okay, so did you guys get?
There'll be one in the middle of some column or row, and then you need two to cover it.
Yeah, I mean, yeah.
Wait, can you just explain it once more?
The whole thing or the induction part?
No, no, the part you just explained, the induction part.
Okay, so you got this, right? We want to prove this implies this.
Yes, yes, I got that. Then we'll have a downward spiral.
Okay, so now you have this cell with four dots. And let's say that this has m of a is equal to what is 5. Okay, so we want to prove that this would imply 5 for n equals 4. So we want to prove this implies 3 for n equals 3. Like this is basically number of tiles.
Okay.
So what we are doing as the inductive step is we are taking this vertex and deleting its row and column entirely. And we're considering the new 3 by 3 grid form, which is formed by this.
Oh, by joining.
Yeah, so you got that, how that works, right? And you also got why the grid satisfies all the conditions.
Yes, I got this. Satisfies.
Okay. So now what we want to do is we want to show that there exists some point such that there are two tiles which are completely in its row and column.
Okay.
Because if we delete its row and column, then we'll be deleting two tiles completely, which would then give the required statement.
Okay, yes, yes.
Okay, and basically for that we use this, that there are at least n plus 1 tiles and there are n points. So one of the points will have two tiles in its row and column.
By PHP. Okay.
Yeah. Okay. Did everyone understand this?
yes, it is quite a neat solution.
Yeah, it's pretty neat.
Yeah, this is very nice for me. So okay, I guess we are done here. We'll go that far beyond time. Oh, so oh, this was PHP, and we are not going to do EV because like EV is bad. Do not do EV. Okay.
What's EV?
Expected value.
Oh,
Why did you just say it's just straight out bad?
Because I mean, the problems from EV are very cringe.
Isn't
Okay.
the algebra at the end?
Okay, wait, I should say this off record. Let me stop recording.